Hi everyone, I am Bahare Shakiba Jahromi from Drexel University. In this video, I'm going to present our work ReMeshGNN, a rotation invariant graph neural network for mesh classification. Shape analysis tasks such as mesh classification, segmentation, and retrieval demonstrate symmetries in Euclidean space and should be invariant to geometric transformation. This means that whether a shape is rotated or translated, its classification, segmentation, and retrieval results should remain unaffected. Rotation invariance ensures that a shape identity and analysis outcomes are stable regardless of its orientation in space. Shape datasets such as ModelNet and ShapeNet contain shapes that have been pre-aligned into a standard orientation. However, in practical scenarios, 3D meshes can undergo random rotations and may not have such canonical poses. Nevertheless, most 3D shape analysis methods do not demonstrate invariance to 3D rotations. As an example, these two methods have been trained and evaluated on ModelNet 4T with pre-aligned shapes. They fail to generalize to models in unknown poses and experience a significant performance drop when trained on aligned shapes and evaluated on randomly rotated shapes. One approach to address this challenge is using data augmentation strategy. We can increase classification accuracy by training our models on data augmented with random rotations reaching to 81.1 and 87% accuracy here. However, the performance doesn't yet match the levels attained with models trained and tested on pre-aligned shapes. Some methods utilize handcrafted features that remain consistent despite rotational changes. Another group of work converts the point clouds into their canonical pose using PCA-based analysis. However, the accuracy of these methods decrease in classification tasks for datasets with non-symmetrical objects where intra-class shapes do not share similar structures. The goal of our research is to develop a representation of 3D objects that remains unaffected by geometric transformations such as rotation without training on rotation-augmented dataset or pose normalization. In this study, we employ adaptively sampled mesh models to represent 3D shapes instead of other popular methods such as point clouds, volumetric grids, and 2D projections. Mesh models may provide higher resolution by assigning more vertices and polygons to complex geometric areas. Mesh models are a useful choice due to their conceptual simplicity, versatility, and efficient processing methods. However, the irregularity and unstructured nature of this representation poses a challenge when applying convolutional neural network to it. A mesh can be represented as a graph with sets of vertices and edges. Each node, edge, and the entire graph is associated with sets of spatial and geometric features. Vertex features include vertex coordinates, normal, and some rotation invariant features such as mean and Gaussian curvature, area, and dihedral angle. Edge features include dihedral and internal angles and edge-to-height ratios. The initial graph features include a histogram for edge length and dihedral angles of all the edges of the mesh. Edge and graph features are rotation invariant. Our rotation equivariant layer uses the node's edges and graph features as input and generate corresponding output features by gathering information from neighboring nodes in the mesh graph. This process is done in 3 steps. First, we update edge feature by applying a feed-forward neural network to each edge, utilizing the edge feature, the invariant features of the end vertices, the distance between incident nodes coordinates, and the cosine of angles between incident vertices normal and the graph embedding as inputs. We observe that all these input features are invariant to rotation and translation, and therefore the edge feature remain invariant to E3 transformations. We split the node feature update into rotation, equivariant, and invariant portion. We update the vertex coordinate and normal using the weighted sum of relative difference between the vertex and its neighboring nodes. The weights are computed using feed-forward neural network, which take the corresponding edge embedding. The embedded normal vector is then normalized. Any rotation applied to input coordinates will result in an equivalent rotation into their difference. Therefore, the output has an equivalent rotation as the input when the coordinates are rotated. The same principle applies to the second equation for normal vector. Therefore, this part of the node feature update is rotation equivariant. To update the rotation invariant component of the node feature, we utilize another feed-forward neural network. This transformation takes as input the node feature from the previous layer, aggregation of edge updates for edges that are incident to vertex, and the entire graph feature. All the input to this function is rotation invariant. Therefore, this part of the node feature update is rotation invariant. In order to calculate the aggregation of node feature, we have designed a novel aggregation function for combining node feature. The input 3D shapes have been scaled to fit within a unit sphere centered at the origin. We divide the range of distance from 0 to 1 into equal intervals, creating these spherical bins or shells, and bucketize nodes into spherical bins based on their initial position and distance to the center. The invariant part of the node feature that belong to each bin are averaged to form this feature vector. We construct a complete graph with n nodes, where each node represents a spherical bin and have feature vector denoted by m. The process of bucketizing is rotation invariant, as it depends on the initial node position and its distance to the center and remains unchanged when shapes are rotated. Then we apply a two-layer graph attention network on the complete graph. Finally, we compute the average of nodes of the complete graph. In the third step of our GNN, we update the global graph attributes using a learnable transformation. This transformation takes the aggregation of nodes computed by our aggregation function, the average of edge updates, and the graph attributes of the previous layer as input. This equation maintains invariance due to its input's rotation invariance properties. For classification, we utilize the graph attribute obtained through this equation. The local pooling layer performs a series of edge collapse operations. Each collapse operation results in an edge collapsing to a vertex, and two pairs of edges from its adjacent faces merge into two edges. We identify the most appropriate edge for collapsing using a scoring function. Then we rank all edges according to this score. Starting with the highest, we perform edge collapse only if it preserves manifold faces. We compute the feature vector for the new edges and also new vertex. Our classification network uses multiple GNNs and pooling layer to facilitate information propagation across multiple hubs. We concatenate the graph features from all layers, thereby directly using all the information from intermediate layers. We use an MLP subnetwork as the final layer. The network is then trained end-to-end to achieve mesh classification. We evaluated our classification network on model Net4T. We conducted 3 separate experiments. We trained the network using the aligned shapes with no random rotation. In the first experiment, we tested them on aligned test samples. In the second experiment, we tested the network after applying arbitrary rotations to the test data. This experiment simulates real-world scenarios where the shape orientation is unknown to the network. In the third experiment, we examined the effect of augmentation on rotation-sensitive methods. Our method achieved comparable results to the prior work. In the first evaluation scenarios, we maintained the accuracy of 90.7 on the randomly rotated test set and outperformed all compared methods without requiring extensive training on rotation-augmented datasets. Similarly, we evaluated our classification network on Shrek 11 and achieved 100% accuracy. Thank you for your attention.